So in the FIR filter, the equation that we are implementing is y of n equals a x of n plus b x of n minus 1 plus c x of n minus 2, okay, and the data flow graph corresponding to this is assumed to look like this. I have a source that produces the x of n samples. That output x of n basically goes into 3 multipliers. I'll call them m0, m1 and m2, and the inputs to those are essentially, one is the direct x of n input, the other is a 1 delayed input, and the other is a 2 delayed input. The outputs of those multipliers in turn go to an adder. Okay. So this was assumed to be one possible data flow graph representation corresponding to this FIR filter. Given that the source node by itself has no other dependency inputs, it can fire as many times as necessary right at the beginning, and based on that, can we sort of come up with what is the minimum possible average iteration period that we can usefully define for this data flow graph. Okay. So what I am going to do is, let's consider a situation where I have unlimited hardware, and therefore I am going to assume that the firing process is going to look something like this. At t equal to 0, S fires n times. Okay. So that essentially corresponds to the firings S0, S1, etc. up to Sn minus 1. Okay. Now let's draw what the data flow graph is going to look like at the end of this process. That is to say, after S has fired n times, what does the data flow graph look like, right? And based on our definitions of what is happening within a data flow graph, essentially our understanding is n tokens are produced by S and deposited onto each of the output arcs or output edges. So what would it look like? It would essentially be something like the same S, M0, M1 and M2 like this, feeding into the adder. So at time equal to 0, if all that has happened is S fired n times, what would I expect the state of the output arcs to look like? How many tokens do I expect on each output arc? From S to M0, how many tokens do I expect over there? How many were there to start with? There were no tokens on the S to M0 arc, okay, but after S has fired n times, I should see n tokens on it, okay. So I'll write that as ND, okay. So keep in mind, this is not n times d or n into d, it is just n delay elements or tokens, right? That d is just a symbol to represent a token, okay. What about the arc S to M1? It already had 1 d to start with, so after these n firings it will now be n plus 1 d. And the arc S to M2 therefore would be n plus 2 d. Okay. Alright, so far so good. Now what I am going to assume is that I can continue firing, right? So S can continue to fire, but I am going to assume that there was some limit. For whatever reason, after firing this n times, I decided to stop. Okay, so S doesn't fire anymore, right? Now at t equal to 1, what are the possible things that can be fired? From what I can see, what are the things that have tokens? Of course, S can fire at any point in time because it has no dependencies, but I'll leave that aside for now. It has already fired n times, let me just stop there. Okay. Now M0, how many times can it fire? It has n tokens sitting on its input. What does one firing of M0 mean? It means basically take one token out of the input, multiply it by that constant A, which is whatever M0 is supposed to be multiplying by, and deposit a token on the output. That token will be A times whatever it read from the input. Okay. Which means that if n tokens are sitting on the input, it can fire n times. Okay. M1 can fire n plus 1 times, M2 can fire n plus 2 times, but I am going to assume instead that all three of them, M0, M1 and M2 fire n times. Okay. So that basically becomes the sequence M00, M01 up to M0 n minus 1, M10, M11 up to M1 n minus 1, and M20, M21 up to M2 n minus 1. Okay, which means that after this process, my data flow graph now looks like this. Okay, I have consumed n tokens from the M0 input. Therefore, how many tokens are left on the S to M0 arc? 0. Okay, nothing is remaining over there. But now there will be correspondingly n tokens on the M0 to A arc. Okay, I had n plus 1 on S to M1, I consume n of them, therefore I will be left with 1 over here and n tokens on the M1 to A arc. And similarly, S to M2 I will have 2 tokens remaining over here and n on the output arc, right? And if I take this further, then what I can say is at t equal to 2, now once again S can fire, M1 and M2 can also fire. M0 is the only one at this point that does not have any input tokens and therefore cannot fire. Okay, but I am not interested in that. I basically want to finish n iterations of this data flow graph. Therefore, what I am going to say instead is that A is now going to fire n times. Okay, so at t equal to 2, A fires n times. Those will be the activations A0, A1 up to A n minus 1, and the resulting graph will basically look like right. Since I have not drawn an output arc for A, therefore there is nothing onto which A is going to send its outputs. In practice, of course, what is happening is A is generating some output, it is the filtered output, okay, which is going to go somewhere. It is just that as far as I am concerned, within this data flow graph there is nothing to represent over there. What this means is that I am now back to my starting point. Or the starting data flow graph, the DFG, right. So after going through n iterations, I have essentially come back to my starting point. Okay. How long did I take? How many time steps have I taken to finish this computation? 3. T equal to 0, t equal to 1, t equal to 2, right. So essentially what I have is, in 3 time steps, n iterations of the DFG completed. So the average iteration period equals 3 divided by n plus 2, by n, 3 divided by n, right. So as n tends to infinity, the iteration period tends to 0. Okay. So what this means in other words is, if I have the ability to process n samples at a time for each of the operations, the first is the source, then there are the 3 multipliers, and then there is the adder. For each of those, if I have sufficient hardware that I can process n samples, at one time instant, it means that based on my dependencies at least, there is nothing preventing me from finishing the entire computation within 3 time steps. And therefore, the average time per iteration of this data flow graph will tend to 0.